Okay, welcome to this session. So we are looking into some simplified versions of osmotic pressure controlled filtration, and we have looked into the first simplified case, there is the no concentration polarization, and we have looked into the system, how the system can behave and prediction can be obtained. The second simplified case we will be talking about is low polarization, and low polarization can be realized by VW by k, exponential VW by k is in the low polarization can be realized when VW by k is much less than 1. That means, again in this case turbulence is quite high, so that the mass transfer coefficient is so Reynolds number will be quite high, very high, and therefore the mass transfer coefficient will be high compared to the permeate flux. So VW by k will be much less than 1, and that will allow us to have an exponential expansion of e to the power VW by k as 1 plus VW by k plus VW by k square of that 1 over factorial 2 here plus other higher order terms. We neglect the, since VW by k itself is less than much less than 1, VW by k square and the higher order terms will be neglected, and this can be approximated as 1 plus VW by k. Now, what we will be doing next? We will be doing we will be writing the film theory. The film theory, if you remember, this is Cm minus Cp divided by C naught minus Cp e to the power VW by k, and this will be replaced by 1 plus VW by k. So, this is a simplified version of the film theory, and then we will be writing Cp as Cm into 1 minus real retention, and then we will be writing the osmotic pressure model as Vw is equal to Lp del p minus del pi, and we have seen earlier how del pi can be replaced in terms of real retention and membrane surface concentration Cm. Now, combining these three equation, we will be getting a simplified version as Vw is equal to Lp del p minus b Rr C naught 1 plus Vw by k divided by Rr plus 1 minus Rr into 1 plus Vw by k. Now, in this case, what you will be ultimately getting? So, ultimately you will be getting a quadratic in Vw. So, all the other quantities are known to us. Lp is membrane permeability, del p is the transmembrane pressure drop, b is the osmotic coefficient known to us, Rr is real retention known to us, C naught is the feed concentration, k is the mass transfer coefficient that will be that we can calculate, and we have seen how to calculate the mass transfer coefficient. So, we can calculate the Vw, and from the Vw one can estimate the so one can directly get the expression of Cm, because Cm minus Cp divided by C naught minus Cp can be expressed. So, Vw can be calculated independently. Let us see now how Cm will be calculated, Cp will be calculated. So, if you look into the osmotic expression of film theory, Cm minus Cp divided by C naught minus Cp is equal to 1 plus Vw by k. We have already got an explicit expression in quadratic form of Vw. So, therefore, this Cm minus Cp can be replaced in terms of Cm. So, this will be nothing but Cm times Rr, because from the definition of real retention 1 minus Cp by Cm. So, Cm minus Cp is nothing but Cm times Rr, and C naught will be nothing, Cp will be in the denominator, Cp can be replaced Cm into 1 minus Rr is equal to 1 plus Vw by k. So, just rearrange Cm. So, this becomes Cm Rr is equal to 1 plus Vw by k times C naught minus 1 minus Rr 1 plus Vw by k times Cm. So, Cm will be Rr plus 1 minus Rr 1 plus VW by K, and here it will be 1 plus VW by K times C naught, or one can estimate the value of Cm as 1 plus VW by K times C naught divided by the denominator RR plus 1 minus RR into 1 plus VW by K. So, VW we have estimated already as a quadratic in the only few minutes back, and K is known to us, C naught is known to us, RR is known to us, and one can estimate the value of Cm. Once the Cm is estimated, then permeate concentration can be estimated as well through the definition of real retention. So, we can have an independent system prediction in terms of permeate concentration and permeate flux for a low polarization case. When the polarization is not low, whether when it is significant, we have already seen that we have to solve two equations and two unknown, three equations and three unknown system by using Newton-Raphson. After combining all the equations, we will be landing up with a single nonlinear algebraic equation, which will be solved iteratively by using the Newton-Raphson method. So, we will be doing another simplification, so that the things will be physically quite significant and apparent to us. The third simplified case will be the low polarization and completely retentive membrane. Low polarization, that is VW by K, is much less than 1, and completely retentive membrane, that means Cp is equal to 0. Cp equal to 0. So, in this case permeate flux will be Lp del P minus del pi will be P C naught B Cm minus Cp, and Cp will be equal to 0. So, you will be having Lp del P minus B Cm, and from the film theory, what you will be getting? From film theory, you will be getting Cm by C naught, because all Cp's are 0. It is a completely retentive membrane, exponential VW by K. So, it will be 1 plus VW by K. So, you will be getting permeate flux is equal to Lp del P minus B C naught 1 plus VW by K. Now, if you bring VW to the other side and write everything in terms of that, so you will be getting Lp del P minus B C naught divided by 1 plus B C naught divided into Lp divided by mass transfer coefficient K. And now, if I replace Lp, the membrane permeability, in terms of membrane hydraulic resistance Rm, then I will be getting a concrete expression of permeate flux as delta P minus B C naught is equal to mu Rm plus B C naught divided by K. So, this expression clearly shows that this is the effective driving force, that is the transmembrane pressure drop, applied transmembrane pressure drop minus osmotic pressure divided by, there will be two resistances in series. One is membrane hydraulic resistance, and there is the resistance due to the mass transfer in the mass transfer boundary layer. So, two resistances in series, that will be appearing in the denominator, and on the numerator you will be having the effective transmembrane pressure drop, which will be nothing but the actual transmembrane pressure drop minus the osmotic pressure that is developed into the system. So, this clearly shows that mass transfer resistance and membrane resistance, they will be acting in series in an actual system. Okay. So, before going into the other variants of solution diffusion model, I would like to now at this point of time, I would like to include or introduce velocity variation technique, or one more technique. If you remember in an earlier class, we have said that there are two ways or two experimental methods to estimate the real retention of the system. Now, we will be really looking into how to we have seen one method already, how to conduct a separate set of experiments, so that the real retention of the system can be estimated by under low polarization condition, that is low operating pressure, low feed concentration, high turbulence. Now, in this we will be looking into one more method to estimate the velocity variation technique, which will be utilizing the film theory model to estimate the real retention of the membrane. Technique to estimate RR of membrane solute solvent system. So, we take recourse to the film theory model and its equation. So, Cm minus Cp divided by C naught minus Cp is equal to exponential Vw by k. Now, next what we will be doing, we will be writing the definition of real retention and observed retention. So, real retention is 1 minus Cp by Cm. So, Cm can be written as so Cp by Cm will be 1 minus Rr, Cm by Cp will be 1 over 1 minus Rr. So, therefore, Cm is nothing but Cp divided by 1 minus Rr. Similarly, from the definition of observed retention, R naught is 1 minus Cp by C naught, and we can estimate the value of C naught in terms of Cp. So, C naught will be nothing but Cp divided by 1 minus R naught. So, now we are going to replace the expression of Cm in favor of Cp and Rr and C naught in favors of Cp and R naught in this equation and see what we get. So, if we really do that, you will be getting Cp 1 minus Cp divided by 1 minus Rr minus Cp is equal to Cp divided by 1 minus R naught minus Cp exponential Vw by k. So, this can be, so Cp will be cancelling out from both the numerator and denominator, and you will be getting an expression of observed retention and real retention and permeate flux and mass transfer coefficient. If we simplify this equation, I am just writing the final form ln R naught divided by 1 minus R naught is equal to ln Rr by 1 minus Rr minus Vw by k. Now, in this expression, if we have the real retention as constant, and let us see how if we change your operating conditions. Operating conditions means here we cannot change the operating conditions in terms of pressure, because the mass transfer coefficient is appearing here, and as we have already seen that mass transfer coefficient is a strong function of Reynolds number, and Reynolds number will be basically a strong function of the cross flow velocity. So, this method is known as velocity variation technique. What we will be doing? We will be applying different cross flow velocity in the system that will alter the mass transfer coefficient. Once the mass transfer coefficient will be altered, the permeate flux will be altered, and once the permeate flux will be altered, as well as it will be affecting the permeate quality. So, observed retention, because permeate concentration will also be altered. So, observed retention will be altered. So, therefore, we change the cross flow velocity and get different values of permeate mass transfer coefficient and permeate flux, and then we plot ln R naught by 1 minus R naught versus Vw by k. So, now if we plot ln R naught divided by 1 minus R naught versus Vw by k, you will be getting a curve something like this. So, similarly, actually this will not be hitting the y axis, the curve will be something like this, and similarly it will be for the other values of mass transfer coefficient will be getting this. So, ultimately all these points will be going to the intercept r naught by 1 minus r naught. So, this for a particular k, that is for another particular k. So, we will be getting the from the intercept. What is the intercept? The intercept is ln rr by 1 minus rr. So, from the intercept one can estimate the value of real retention. So, rr can be estimated. So, what is the drawback of this system? The major drawback of this system is that the experiments should be very accurate. If there is slight inaccuracy in the experiments, then in the log scale this will be even magnified, and therefore, that will be giving a very wrong estimation. So, there will be more number of experiments one has to conduct, but not only that, not only the more number of experiments, the experiments has to be very accurate. Then only one can get an estimation of real retention, appropriate estimation of real retention by this velocity variation method. Okay. So, next we will be looking into, as we have discussed, that the third equation for let us look into once again the modeling equation for the osmotic pressure control filtration, one dimensional model. So, we have the film theory VW is equal to k ln Cm minus C naught, Cp minus C naught. We have the Darcy's law VW is equal to Lp del p minus del pi, and we have two equations, two unknown Cm, Cp, VW. These are the three unknown and two equations. The other equation is the connection between the Cm and Cp. Cm and Cp, and we have already seen that one way of connecting Cm and Cp is the real retention, that is nothing but a partition coefficient between across the membrane of the solute partition coefficient across the membrane. Now, we have already seen all the formulations and the method for solving this third equation to get a system prediction of the system performance. Now, what we will be doing? We will be replacing the expression of real retention, that will be more valid for the ultrafiltration system, and various cutoff ultrafiltration system by the solution diffusion model for the reverse osmosis and nanofiltration system. So, real retention is a concept which will be more valid for the ultrafiltration system, but for the reverse osmosis and nanofiltration we won't be able to use the expression of real retention as a partition coefficient 1 minus Cp by Cm. We have to use the other variants of the connection between the Cp and Cm, that is the solution diffusion model and its various variations or modifications. So, first we will be talking about the solution diffusion model for reverse osmosis and nanofiltration system. For RONF system. So, now let us look into what are the various governing equations. So, one equation will be the film theory, is VW is equal to k ln Cm minus Cp. So, this is wrong, Cp C naught minus Cp, Cm minus Cp divided by C naught minus Cp. The other one is the Darcy's law, which is nothing but the solvent flux through the membrane, VW is equal to Lp del p minus del pi, and the third one is the solute flux through the membrane, that is the solution diffusion model. So, these will be giving you the solvent flux through the mass transfer boundary layer, solvent flux through the porous membrane, and the solute flux through the porous membrane. VW Cp is equal to B Cm minus Cp. So, we will be having three equations and three unknowns VW, Cm and Cp, and can get the system prediction. So, I will just give a a small algebraic manipulation in order to solve this set of equations. So, V w can be the solvent flux through the membrane can be written as V w is equal to L p del p minus del pi. So, this will be, if you take L p out, L p del p out, so it will be giving 1 minus del pi, and del pi is let us say pi is equal to A c. So, del pi will be basically A by delta p C m minus C p. So, I write V w is equal to V w naught 1 minus alpha C m minus C p. So, this is my equation number 1. And what is V w naught? V w naught is basically L p times del p. It is a pure water flask, pure water flux. And what is the parameter? Alpha. Alpha. So, this will be V w naught will be known to us, because L p is known to us and delta p is the transmembrane pressure drop. So, what is alpha? Alpha is the parameter A by delta p. So, it is non-dimensional. So, that will be equation number 1. Then we will be equating this with the film theory equation. So, V w naught 1 minus alpha C m minus C p will be equal to K ln C m minus C p divided by C naught minus C p. So, this will be the combination of the film theory and the osmotic pressure model, Darcy's law. So, I write it at equation number 2. Then we will be having the solution diffusion model for the solute flux through membrane, that will be V w C p is equal to B C m minus C p. So, now we can combine these two equations, and finally, we will be getting into this. So, we will be combining the equation number 3 solution diffusion model and Darcy's law, that is equation 1. We can combine these two equations and see what we get. If you combine these two equations, you will be getting V w naught 1 minus alpha C m minus C p is equal to B C m minus C p divided by C p. So, this equation can be written in this form: 1 minus alpha times C m plus alpha times C p is equal to beta C m minus C p divided by C p, where alpha we have already defined and beta is B by V w naught. Okay. So, from this equation, the membrane surface concentration is obtained in terms of permeate concentration. So, from this we can get C m membrane surface concentration as a function of permeate concentration C p into 1 plus beta plus alpha C p. Now, this expression of C m can be put into the equation that we have already talked about, equation number 2. We are going to put the value of C m that we have obtained in this equation number 2. If you really do that, put into equation number 2, you will be getting one nonlinear algebraic equation in the form of, I will be giving the final expression beta V w naught alpha C p plus beta minus k ln C p divided by alpha C p plus beta into C naught minus C p is equal to 0. Again, this expression is nothing but a nonlinear algebraic equation in C p, and again one has to take care, go by a Newton-Raphson method iteratively. So, one has to have an iterative solution of C p and the method can be used as Newton-Raphson method. Once you get the value of Cp, you will be getting the value of Cm. Cp is equal you will be getting because from this equation you will be getting the value of Cm, because Cp you have already estimated. Once you know the value of Cp and Cm, then one can go through the film theory equation and can get the expression of permeate flux. So, again in this method also we can land up with 3 equations. Only difference is the definition of real retention, which basically acts as a partition coefficient between the membrane surface concentration, solute concentration in the membrane surface and in the permeate, will be replaced by the solution diffusion equation, which is basically nothing but the solute transport equation for the solute flux through the membrane. And then again these 3 equations can be solved and can be recast in the form of a single equation, which will be algebraic nonlinear equation, and that can be solved by using an iterative method, and by that one can get the permeate concentration, membrane surface concentration and permeate flux ultimately. So, I will stop here in this class. In the next class or next session, we will be looking into the other variants of solution diffusion model and how to use this solution diffusion model, where there will be modifications in it in order to get the system prediction perfectly. Thank you very much.